Hilarious.
Okay, guys.
There were a lot of favorite ways to do it.
Way too much.
So I told you, today we're going to look at logarithms. I know we are not super comfortable with them, but we need to get comfortable. All right. So,
why are you emailing me in class?
why am I emailing you in class?
I'm getting updates for class now.
Oh yeah, sorry, because we're posting video. Sorry, I forgot to post it at the end of class yesterday. So that's why today. And why is it wet? All right.
Oh no. Emma, why is it wet?
My water bottle's spilled.
Yeah, it better be water.
Yeah.
Okay. She did have to go to the bathroom, she said.
I love this class.
Oh man.
All right. Properties of natural logs and exponents, I guess we'll say too, because we also need to know exponents. Okay. So let's look at exponent properties first, just to refresh our memories some. Okay, so exponent properties. First, something like a to the 0. So, and let's just call a is a real number. Okay. Ooh. A also is not equal to 0. That's important. Okay, so what is a to the 0?
1.
1. Beautiful. Okay, it is Juan.
Never quite understood that rule, but yeah.
Why is a to the 0
I
1?
need to explain it.
It just is.
It's just.
Well, there is actually, like, you can kind of like argue it. Let me do it real quick.
We don't need to go. Okay.
It's super quick. Watch. It's so easy. 3 to the 3rd. What does that mean?
3 times 3.
3 times 3 times 3, which is equal to 27. Okay. 3 squared. What does that mean?
3 times
3
3.
times 3, and that gives us 9. Okay. 3 to the 1. 3, which is 3. Now 3 to the 0. We're like, what does that equal? Well, follow the pattern here.
Yeah.
As we lower our exponent by 1, what are we doing to the actual value? Dividing by 3, right? So lower 3 to the 3rd by 1 power, 3 to the 2nd, we take 27 and divide by 3 to get 9. Lower 3 to the squared, 3 to the 2 by 1 power to 3 to the 1, and we go from 9 divided by 3 down to 3. So it only makes sense then that we should continue that pattern of dividing by 3 to get then 1. Now, even then, like, let's lower the power even once more. Again, what does that equal? Well, following the same pattern, what do we do? What's 1 divided by 3? 1 over 3, or 1 over 3 to the 1. Do it once more. 3 to the negative 2. What's 1/3 divided by 3? 1/9, which is really 1 over 3 squared. So there you can see that whole, like, negative exponent goes down to the denominator idea.
Yeah, but that's
It all is working on a pattern.
That's just like a pattern, like with like 3 to the 1, 3 to the 2. You can actually like write it out like 3 times 3 with the other. With everything else, you can't really explain why.
You're right, you can't, but it's exactly, but it's based off of the idea of the original definition of what the exponent means.
But like, can you even like prove that actually that if like you can't even or
I imagine yes, it is proved somewhere.
Yeah, I feel like
I'm not sure where, and you're right. I can see what you're saying, but that's the basic kind of like reasoning behind it. Okay, so for example, I think like if you also think about like the number I, square root of -1, right? Like I think there was a point in mathematical history where they didn't even bother with something like that because it's like, well, this never really shows up, but now I actually does show up in certain applications, and so they do need to like actually, you know, develop the idea of I. Similarly to calculus, calculus did not start out as, you know, a well-formed, you know, mathematical kind of like system. It was like, well, we think these things should work, and then they kind of did, but then, and they kind of used the, you know, people kind of used those like rules or whatever, but then like exceptions started to show up, and so calculus needed to be like formalized. So, and formalizing math involves proofs and all that good stuff too, and defining things and stuff. So, anyway, moving on.
And we're just going to course math now.
A to the x times a to the y should equal what?
A to the xy.
No, a to the x plus y.
Oh, yeah.
X plus y. When you multiply numbers that have the same base, you add exponents. Add exponents. Which again, this makes sense. If I have 3 to the third, and I multiply that by 3 to the second, well, if I expand this out and write it like, you know, how we know to, it's 3 times 3 times 3, right, times 3 times 3. Sorry, 3 times 3 times 3 times 3 times 3. Okay, right? But then it's just 5 3s, so it gets 3 to the fifth. Well, how can we go from 3 and 2 to 5? And you add them, and you get 5. Okay, so again, it's kind of a... Intuitively, it makes sense that it would work that way. And by the way, should you be on your own, should you be in the wild, right, doing problems, and you forget, oh man, I got a number, I got a, like, a to a power and a to another power, am I supposed to add here, or am I supposed to multiply here? Do a little, like, over here, convince yourself, like, do a little problem, like, all right, let's say I have 3 cubed, let's say a is 3, and I have 3 cubed and 3 squared. When I multiply those, oh, that should be 3 to the fifth, you know, not 3 to the sixth, right, if we were trying to multiply those. So do a little side problem there to kind of convince yourself whether you're right or not. All right, a to the x to the y. What's that equal to? Power to a power, you multiply. So it's a to the xy. All right. How about if we have like ab to the x?
It's equal to ax.
We can say that's equal to a to the x, b to the x. So you can distribute powers, right? You can think of this like being a to the 1, b to the 1, and the x can distribute to both those ones there. So you get a to the x and b to the x. All right. Again, this is mostly review, I would imagine. So, all right, how about a to the x over a to the y?
It's equal to a to the x.
Yes, as a single, excuse me, base, a to the x minus y. Okay. How about a over b, that quantity raised to the x power? What else would that be equal to? Say a to the x, right, over b to the x.
No.
What do you mean by just, oh, I see what you're saying, because, well, but the bases are not the same. So you can't subtract them. So yeah, be careful about that. I was like, oh, I see what you're saying there. Yeah, I had to think about it for a second there. Yep, right. So yeah, be careful. Same base. If a is not is equal to b, then yes, it would be just 1. All right, and then a to the negative x we know is equal to what?
1 over a to the x.
1 over a to the positive x. Very good. All right, we also should be kind of familiar with what an exponential's graph looks like. So, for example, if I have y equals a to the x, and I want to graph that, okay, and this is just a quick sketch, okay, because it's obviously generic because it's a to the x. But if my x value is 0, what is my y value going to have to be? Right, 1, right? If I plug 0 into my x value, a to the 0 is 1. So, right there, okay, I have to have the point 0, 1. No matter what the a value is. So, for example, if this is the e to the x, if this is e to the x, guess what? Y equals e to the x goes through, has a y-intercept at 0, 1, because e is just a number, right? E is a number. Even though it looks like a letter, e represents a number. And so any number to an x like that, it has a y-intercept of 0, 1. All right? And so then, for a values greater than 1, all right, it will look like this. Like that. It will grow exponentially, right? So for example, this is just like e to the x. E to the x's graph looks very much like this. Okay. If we graph y equals a to the x for 0 less than a less than 1, so these are like fractions, right? Like 1/3, 1/2, 1/4. Fractions are between 0 and 1. Okay. Still at 0, what will the y value be? 1. But now, how will this graph look? So it's going to look, I think what Anna was pointing at, like, were you basically saying flip this, Anna?
Yeah, because
Yep.
put the 0, 1 on the
Yep, yeah, right, exactly. So it's going to go down like this. The idea being here that as we use larger and larger x values for x, this 1/2 raised to like the 100th is going to get teeny tiny, right? But whereas when you use negative values, that becomes then 1 over that fraction, which then it's going to get bigger and bigger and bigger. So it makes it kind of flip like that. Okay? So that's the idea. What is the domain of either of these two functions?
X is greater than 0. Or 0 less than x.
Domain?
I mean,
I mean, not x, excuse me, it's all real numbers. So
yeah, it's all real numbers for the domain. The domain is all real numbers. What's the range?
Would be x must be greater than 0.
Y must be greater than or equal to 0. Or greater than 0, sorry, just greater than 0. We actually never get to actual 0 here. Yeah, y must be greater than 0. All right, so yeah, the domain here is all real numbers. I guess I'll put that like here. Domain, all, and I'm going to use a symbol for real numbers. Range is y greater than 0. Okay, so for those two. By the way here, so I guess I didn't talk about negative numbers, but the negative numbers we don't really graph, because then you'd have a really weird function if you graphed like a negative 1/2 to like the third, because it would like either not it would be like positive, it would like jumping to positive and negatives and stuff. I don't know, that'd be weird. So, but what if a was equal to 1? What would that look like if a was equal to 1? What would this graph look like? Be a horizontal line at 1, right? Because 1 to a power, well, it doesn't matter what the x value is, 1 to the any power is going to be 1, so it'd be a horizontal line. So that's why we don't really talk about that one, because it's kind of, silly. Okay, so there's that. Any questions there? All right, good. So let's get into then some like e stuff. So remember, e to the x is a special exponential that we kind of highlight, right? So non-special exponentials, 2 to the x, 3 to the x, 10 to the x. We don't really talk about those that much. But e to the x is one, a special one we kind of highlight based on the fact that, we derived that number e, from it's a very important number. All right. Natural log of x, okay, that is the inverse of e to the x. It's like the opposite, kind of undoes it, right? Square roots undo squares, cube roots undo cubes, addition undoes subtraction, multiplication undoes division, stuff like that, okay? Natural log of x and e to the x are opposites of each other. They undo one another. All right. Remember, natural log of x is the same thing as saying log base e of x, right? Those two things are like the same. I'll put that in like kind of parentheses. So it's log base e of x. And when you first learned logs, you just learned the word log there. But instead of writing log base e of x, we just use natural log like that. Let's see here. The way we come up with logs in the first place We take a number in exponential form, like where logs come from in the first place is we take something in exponential form and we convert it to an equivalent logarithmic form. Right, you remember, so maybe you have like an exponential written like this, but then you can rewrite it as log base A is equal to x, right? The y goes inside the log, base A, and then the x is the power there. Okay, so using that idea then, for example, the natural log of 1 should equal what?
Natural log of 1 is
So let's think about this. What is the natural log of 1 equal to? Well, let's think about that. That's log, natural log is the same thing as log base E of 1, and we want to know what does that equal. Let's convert that to exponential form. So it becomes e to the blank equals 1. So yeah, it's 0. So natural log of 1 is 0 because e to the 0 gives us that 1. So when you do a natural log, it's like, what power of e gives us 1? Well, the answer is 0. Bless you. So natural log of e, what does that equal? What is the natural log of e? It's 1. Yeah, okay, so let's just convince ourselves that's right. Remember, natural log is log base e of e. We don't know what that equals. Again, using the exponential form here, just kind of help convince ourselves. We're going to rewrite this in exponential form, so it becomes e to the blank equals e. Well, if e to the blank equals e, e by itself has an exponent of what? 1, so that means it has to be 1. And so natural log of e is 1. Remember, that's also, you can kind of think of this as like the whole idea. What is this e here? It's got a power of 1. What do we say that natural logs and e's do? Cancel each other out, so we're left with just a 1 there, right? So that would make sense then if I say the natural log of e to the negative 1 should give me what? Negative 1, because the natural log and the e cancel each other out, and that's true. Okay?
So if it's natural log of e, the answer is whatever's in this.
If it's natural log of e to the pi,
The answer is pi.
the answer is pi. That's it.
Natural log of e to the 10, the answer is 10.
If it's natural log of e to the cosine x, it's cosine x. Okay? Alright. Properties of logarithms. We love these too. So for example, natural log of the product xy is equal to, when you have a product inside a logarithm, what does it become outside the logarithm? Ooh, crickets.
It becomes ln x plus ln.
ln x plus ln y, exactly right. Okay. Natural log of x over y, then it would make sense, would be what?
ln of x.
Natural log x minus natural log y, exactly right.
It's all coming back to me.
Good.
Oh, yeah, it's just a real promise all these.
She said you're on your own. JK,
Yep.
she taught that stuff. to me, guys.
She was like, here, read the book about this.
Yeah. All right, natural log of x to the z. When you have an exponent like this, what can you do with it? You guys remember that? Yeah, it goes out front, exactly right. So it becomes z times the natural log of x. Again, this is not, by the way, these are not taking the derivatives, right? These are just being rewritten. There's no calculus here at all. This is all pre-cal, okay? All we're doing is just rewriting. These are all equivalent things. No derivatives or anything like that.
That's why when it's ln e, whatever's up front is the number because it's just multiplying them.
Exactly right. So, if you guys didn't hear that, let me just connect that to you here real quick. This property, okay, Ryan was pointing out, this property connects back to the fact that, for example, here, natural log of e to the pi is just pi, because what can we do with this pi? It goes out front, and then what's natural log of e? 1, so it becomes 1 times pi or just pi. Okay, that's the idea there. Yes. Okay.
No, because it's not the e.
All right, so let's use these properties here. Wait, did I hear a question? Sorry.
There would just be a z.
Yeah, it would not just be z because we don't know x is not like an e power, it's just a number x. So, all right, so let's do some examples here using these powers. We're going to expand.
Tom, put on crash.
So, for example, the natural log of 10 over 9. I gotta take a time. The natural log of 10 over 9. How could we rewrite that? Connor?
Natural log of 10 minus the natural log of 9.
Natural log of 10 minus natural log of 9. Now we can actually rewrite this one more step here, just to quote-unquote simplify it a teeny tiny bit more. 9 is also what? 3 squared. So we could rewrite natural log 9 as natural log of 3 squared, which what can we do with this 2? It can go out front. And then technically we could also say 10 is 2 times 5, and we can make it natural log 2 plus natural log 5 minus, but, I don't know if it really, I think it kind of depends what you're looking for there for simplification's sake, but this is sufficient. We did expand it, but we can also, notice we can also break that 9 into 3 squared, bring the 2 out front. So just understand that's a thing we can do. Okay? Let's see here. How about natural log of the square root of 3x plus 2? How can we expand that?
Well, actually,
Negative exponents.
Or fraction exponent.
Mm-hmm. Fraction exponent. Square root is the same thing as what power? To the 1/2. And that 1/2 can then go out front. So we get 1/2 natural log of 3x plus 2. Can I break up this addition here inside the natural log?
No.
No. We do not have a property over here to break up addition of the natural log.
Well, you say that makes you think there will be a property. No,
Nope. I wasn't even leading towards the property. It does not break up addition inside of natural log.
That's what he wants.
That's right. Okay. So there's the idea.
Cool. Radical. Ready. Nose it does. Class is over.
Mr. Wood, why?
And then you woke up. Okay. Wait. We're going to do some exponential equations now, because this is where some of the nitty-gritty that we really want to make sure we have down. We'll just do 2.
Oh, yes. Here we go. I just picked up my stuff right here. I just wanted to, wait a minute.
That's not a writing utensil. That's for hair.
Hate it when I mistake that.
Right? Start combing your head with your pen.
I love this stuff.
7 equals e to the x plus 1. We want to solve for x.
Well, 7. Oops. Already missed e x plus 1. ln of 7 equals x plus 1. That just cancels. ln of 7 equals x plus 1. Ooh, I did it. Do you really want to go? I took a picture this morning. Little monkey head.
Jack, how do we do this? So you want to do natural log to both sides? Yes. Natural log of 7 equals natural log of e to the x plus 1. Okay. Natural log of 7, can we simplify that at all, Jack? Can we simplify that at all? ln 7?
No.
Yeah, not really. Mm-mm. What does this simplify to? What can we do with this x plus 1? Yeah, the x plus 1's a power, right? So it can go out front. I mean, if I really want to write this out, I can. We're left with natural log of e, but we know natural log of e is equal to what? 1. And so it just becomes x plus 1 equals natural log of 7. And then to finish solving here, Jack, what do we got to do? What do our directions say to do? How do you solve for x? Yeah, subtract 1 from both sides. Okay, natural log of 7 minus 1 equals x. This is a fine answer to leave. If this is like, example, like a free response question, or like maybe even multiple choice sometimes, you might leave your answer like this and not have to get a decimal, okay? Leave it like that. I would recommend not actually doing this work out and getting a decimal answer unless it asks you to approximate. And when we do approximate decimals, how many decimal places do we go to? 3. You may round or truncate, which just means you cut off the digits after the third digit. Okay, you don't have to actually round it if you don't like rounding. But be consistent.
Is that ln 7 minus 1, or can it just be ln?
So it's like ln 7 minus 1. Yeah, we can't make that 6 because it's not natural log there and stuff like that. Yep, I do have it. You're welcome. All right, one more here, and then we'll go into the actual derivatives and stuff.
Take a stretching break after.
Mental stretch.
I've been thinking this for like 20 minutes.
Yeah, but I'm struggling.
Man up, Christian, come on.
Drifting
Is that it?
Yeah, that's all for that equation right there.
Long way, I'll get out of this. I think you're running low and right off the switch.
Oh, it might be. Did you push down enough on the tip there?
Yeah.
That also helps. All right, Mac. We have our we have our x in here inside the natural logs. So in order to solve for x, we got to get into this x somehow. We probably need to get rid of this natural log. What do we use to cancel out natural log? E. So we're going to e to the power of the left-hand side equals e to the power of the right-hand side. Okay, it's kind of like hard to say verbally, but it's like e to the power of the left-hand side equals e to the power of the right-hand side, just like that. So I just put the little e down there. We're going to e both sides. So the e and the natural log cancel out. So we're left with 2x minus 3 equals e to the 5th. All right, e to the 5th, right, is going to be some funky number. By the way, e is approximately what decimal? Yes, it's important that you have that down. Just like you have pi is about 3.14, you should have down that e is about 2.7 something. 2.72? Okay. Okay. So 2.72, okay? If you can have just 2.7, that's going to be awesome, okay? You need to know E is 2.7. E, I'll write it down here. E is approximately 2.72, we'll say. Okay, you should know that, just like you know that pi is approximately 3.14. Okay? It will help you later, perhaps on a future assessment, to know that. All right. So we add 3 to both sides, right? And then last step here, Mac, what do we got to do?
Hold on.
I'm sorry.
What did I do?
Divide by 2. So we get x equals e to the 5th plus 3 all over 2. Or if you like, we can like divide that up and make it 1/2 e to the 5th plus 3/2. If you want to like break up the fractions, either one of those is fine.
No.
Or not.
Mr. Whitmire?
Yep.
E is 2.718.
Yeah, okay. That works. All right. Questions? Are you ready for some calculus now?
No.
So that's what we call throwback notes. Okay, so there you go. Throwback to pre-cal.
Good time.
Can we just stay in pre-cal? I don't know. I think pre-cal is tougher than calculus, but that was just me, maybe. I thought so.
I have like 10 pages left in my notebook.
Well, one of them allows you to be good at the other one, probably.
You can buy notebooks for pennies on the dollar.
Derivative of the natural logarithmic function. All right, let U be a differentiable function of X. Okay, let U be a differentiable function of X. The derivative with respect to X, remember that's what that symbol means, d over dx, the derivative of natural log of X with respect to X, that's the dx at the bottom, with respect to X, is equal to 1 over X. Okay, and that is only for X values greater than 0. Why do you think we have to put that stipulation in that X value has to be greater than 0? Can we take the natural log of a negative number? So let's think about that. Natural log, let's say I want to try and find like the natural log of negative 2.
You didn't put a parenthesis.
I have no idea what that equals, so I'm just going to put question mark. All right, now let's see here. Natural log of negative 2 equals question mark. That's the same thing as saying log base e, right, of negative 2. We want to know what that equals. Then we take that, we say e, we write that in exponential form, which we're more familiar with. E to the question mark equals negative 2. What's the value of e? 2.72. So we're trying to take a number like 2.72-ish, raise it to a power, and get negative 2. What's the problem with that? Can't take a positive number, raise it to an exponent, and then get a negative answer. Can't be done, right? Won't work. So that's why natural log, you can't take the natural log of negative numbers. There's no value. They don't exist, okay? So that's why you have x greater than 0 there.
What was the change of base formula again?
It's just, well, I mean, you do whatever base you want to change it to. So, like, for example, if you want to find, like, natural log of 5, then you can just do, like, log 5 divided by log e. It's log of the big number divided by log of the base number there. And whatever logarithm base you want to use. So we don't need to know that for this class.
Okay.
Good news. All right. So notice here, this is just for natural log of x. So this is like for literally the variable x. Now if I do it in a more generic sense using u, okay, so now u could be like cosine of x, u could be x squared, u could be x squared plus x plus 1, u could be a function now. It's still going to be 1 over u, but then by the chain rule, what do we then have to multiply by? U prime. And again, that's for, if u is greater than 0 there. U prime is outside the denominator. So basically, the derivative of natural log of something is 1 over that something times the derivative of that something. This is just for if you just have plain old x inside the natural log, it's 1 over x. But if you have like natural log of cosine of x, it's 1 over cosine x times the derivative of cosine x.
Wouldn't that really just be u prime over u?
Yeah, you could rewrite it as u prime over u if you wanted to. Yeah. All right, so let's see some examples here. So let's find the derivative with respect to x of the natural log of the square root of x. All right, we see square roots, so immediately we should think we should do what? Change it to x to the 1/2. Now we have kind of two paths here. Any ideas about one path that we could do? Yeah, bring out the 1/2. The other path would be that we take the derivative as it's currently written. We would write it as 1 over x to the 1/2, then times the derivative of x to the 1/2, right? But I like simplifying this derivative before we then take simplifying our natural log here before we take the derivative of it. So yeah, it becomes the derivative with respect to x of 1/2 natural log of x. That'll be much nicer to differentiate. Okay. So that 1/2 is just a coefficient, so we kind of, not ignore it, but we don't need to worry about differentiating it. What's the derivative of just natural log of x?
1 over x.
So it's 1/2 times 1 over x then, which is just 1 over 2x. There's the derivative. So this one, we can simplify. Simplify it first, then take the derivative. It helps.
Can we do it the other way?
You want to try the other way?
Yeah, see how long.
Sure. I'm up for a little sweat here. Let's see. So x to the 1/2. So if we take the derivative now as it's currently written, the derivative of this will be what?
1 over x to the
1 over x to the 1/2 times
1/2 x
1/2
x
x to the
negative.
negative 1/2. The derivative of what's inside there is, Okay, it's not terrible. It looks worse than it really is. Watch. Where does this x to the negative 1/2 go?
To the bottom.
To the denominator of that second fraction there. So it's going to be 1 over 2 x to the 1/2. But what's x to the 1/2 times x to the 1/2? What do you do when you multiply? You add exponents. So what's 1/2 plus 1/2? It's 1. So it becomes 1 over 2 x to the 1, which is exactly what we have right up there. Questions? Let's do another. I am. I love calculus. It pays the bills, but I also do really love calculus as a topic. Okay.
You like see calculus in high school, and you were like, this is what I want to do.
Actually, yes, I really loved calculus when I was in high school.
Really?
Yep. Like when they showed position, velocity, acceleration, how they were all related, and also how calculus brings together pretty much every math class you've taken up to this point. It brings everything together, except for statistics. But
Not a good.
I think it's great.
Finally.
It's always like, finally, it all makes sense now. Everything I've been working on for the
That
past
helps.
16 years of my life is just conglomerated together to make one
Life makes sense.
horribly
now.
different.
All right, Brandon,
Big word.
derivative here. What do you think?
You want the answer?
No, please. The first next step. Can we simplify this at all, Brandon, before we start? Yeah, no, we can't. Okay, this x squared maybe, but why can't we simplify the x squared? Pull that 2 out front.
Well, you can't pull it out front.
Why can't we pull the 2 out front?
You can't present the exponent of the entire quantity.
All right, it's not the exponent of the entire quantity. Please, guys, listen. If you're exponents in here, brain is zoning out right now. Focus up for this real quick, okay? And then stay focused because obviously I don't want to lose you. But anyway, this square here we cannot pull out with the way this is written because only the x is being squared, not the entire quantity. But the entire quantity is what is inside the natural log. So if this were the quantity, x plus 1 squared, then yes, the 2 could go out. But since it's x squared plus 1, since this quantity is not being squared, that 2 can't come out. It has to stay the way it is. So, Brandon, that being said, when we go to take the derivative, what's the derivative of natural log of x squared plus 1?
You want step between or two?
Yeah, give me the very next step, please.
1 over x squared plus 1.
Yeah, so 1 over what's inside times
Derivative.
derivative of what's inside. 2x, exactly right. Which then yields, when we simplify,
2x over x squared plus 1.
yeah, 2x over x squared plus 1. Voila. Okay? Questions on that? Am I moving too fast? Just fast enough? Too slow?
When I think about it, the other calculus class is doing this the second half of the first day of school.
They probably don't do as many examples and stuff as we do, obviously.
Probably.
So in a way, we're getting a better digestion of the information.
I hope so.
We're getting more fiber.
Mm-hmm. Okay, the derivative of x times the natural log of x. Can we simplify this at all before we take its derivative? Not
Well, it could be
really,
L1
no.
X to the X, but
Yeah, we
that
could
would
bring
be
the
more
x
simple
inside,
for
make it x to the x, but yeah, I don't think that make it simple. I think it make it more complicated. We don't even know x to the x. Whew. We don't even know. Okay? So, let's see here. The derivative of x times natural log of x will be 1 times 1 over x then.
No, product rule.
Nope.
Product rule.
Product rule.
Disgusting.
Oh, ew, bro. Why?
Okay. This is x times natural log x. Product rule. So, there's our first quantity, there's our second quantity. So it's the first x times the derivative of the second, 1 over x, plus the second, natural log of x, times the derivative of the first, 1. So we get 1 plus natural log of x. Keep your eyes peeled, guys. It's those simple ones that get you, because they seem so innocent. But they're like, nope, product rule. Okay? You look at it and you're like, oh, this is easy, no big deal.
Wrong.
It's not.
That's the wrong.
Product
Learn
rule.
to thinking. Calculus, if it looks easy, is
Right, right. I'm suspicious because I found that very easy. All right, I must be wrong. All right, one more here. I'm going to have you guys try one. Thank you. Mackenzie, this is for you. And it's for right now, it looks like. Time to get some counseling. Okay. Again.
Wait a minute.
Oh, chain rule.
Chanda, can I bring this 3 out front? This 3, and so let me just clarify here. The 3 is, so it's natural log of x, that quantity is being cubed. This 3 we cannot bring out front because where would this 3 need to be in order for us to be able to bring it out front? Inside with the x. So it would have to be natural log of x cubed, then we could bring the 3 out front. Because it's a quantity cube, as a simplification, we're not going to bring the 3 out. But then when we go to take the derivative, what's the outermost layer here of our little function, I guess we'll say? Chanda. It's the to the third. And so when we take that derivative, what is the derivative of something to the third? So Chanda, I'm going to have you keep going. Sorry. What's the derivative of something to the third? 3. And in this case, times what? Natural log x, quantity to the 2. Right, don't forget, guys, it's very easy. For whatever reason, students like, oh, bring that 3 out front, but then they forget to lower the power by 1. Please don't do that, because I see it happen all the time. People bring that power out front, and they forget the power to rewrite the power, because they're like busy rewriting, I guess, the little base there, whatever. Okay, great. Are we done?
Derivative.
No, then times what, Chanda? Very good. The derivative of what's inside, which is 1 over x. Okay. So there it is. I mean, if you want to put it all together, you can. I don't know if it's really any better or less ugly this way, but that's, you know, like your opinion, man. So there it is. Okay? All right, maybe you guys want to try.
Oh, nice. Nice. You really want to go?
Mr. Wood, why do lumberjacks make really good musicians?
Because they, I know why. They have natural logarithm.
That's
probably-
Is that right?
Yeah.
There actually is a calculus joke, but we won't be able to do it until we learn integrals. But it involves,
You won't understand.
it involves, you know, natural logs and stuff like that, so. So it wouldn't make sense, but. Yep. There's also calculus pickup lines.
Dude, I need to Google that.
I don't remember the one. But it's like, girl, are you differentiable? Because I want to be tangent to your curves. I know. Irresistible, right? I know.
It would work on a like a really.
I mean, the
Girl.
calculator belt
Like, oh my God.
really helps that too.
That's why.
Firework blast.
All right, let me calculate the derivative. Beep, 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 beep.
What girl would say no with that?
I know.
Come on, let's be honest.
Hard to believe.
You really want to go.
Oh my goodness. All right, Brittany.
Boy, I don't think you can bring that one out.
Brittany, can we rewrite this at all before we take the derivative?
You can.
Okay, so this is really the natural log of the quantity 2x plus 1 to the 1/2, and then can we simplify that any further? Yeah, bring that 1/2 out, which is not taking the derivative yet, right? We're using logarithm properties to bring that 1/2 out front. Now the 1/2 out front, so we're going to take the derivative now, and what do we get there, Brittany? We're going to have the 1/2 still, right? Times, what's the derivative of natural log of something? 1 over what? Yeah. Times the derivative of what's inside, which is 2. So the 2 and the 1/2 cancel, and you're left with 1 over 2x plus 1, yeah?
Yeah.
Oh, yeah.
Oh, yeah. Ever seen that movie Fargo?
Oh, yeah.
Yeah. Oh, yeah. You betcha.
You betcha, yeah.
Oh, yeah.
Okay.
You betcha. I think we got ourselves a murder, huh?
We're good there on that one? Questions? Question.
That hurts. Oh yeah.
Chain
You
rule.
betcha. You betcha, old buddy boy.
Yeah, bring the 1/2 out.
Oh, man.
Right there, bring that 1/2 out front. It'll make it easier. You can do it that way, you can do it, but it's going to make it more complicated. Shh. Brandon, question.
Why, after you take the 1/2 out, is it not like the derivative of it? Why not take a derivative of 1/2?
Because 1/2 is a coefficient. Like when you take the derivative of 2x squared, it's the same thing as taking the derivative of x squared and then multiplying that answer by 2. Coefficients you can kind of like just bring along for the ride and multiply at the end. All right, I have 2 more I want to show you here. I was wrong when I said I only had 1 more. My mistake. But it's going to be worth your while, and I know we're like really close to the end here, and I apologize. I'm not going to give a lot of homework time again tonight, but I want to get these in because these are fun. All right.
I love these.
F of x equals natural log of x times
It's okay.
What?
What are you trying? What are you trying to hold?
that's our function, and we want to take the derivative of that.
Sure about that.
Positive. 2x cubed. 2x cubed. And the denominator is 2x cubed, guys, folks. Okay, so Caleb, do you see any way we can simplify this before we take the derivative? For example, I see, within this natural logarithm, I see division. What can we change division to inside a natural logarithm? Not multiplication, yeah, division, right, can become subtraction on the outside. Division inside the natural log can become subtraction on the outside. I'm also going to change the square root to x to the 1/2, I should say, power. So, okay, like so. Oh yeah, I'm sorry. I'm going to zoom out some. There we go. You're welcome. Yes. All right, Caleb. Is there any other way we can simplify this, Caleb?
Wait, Mr. Wood.
Whoops, sorry. Question.
Why wouldn't the 1/2 wouldn't be made into a negative?
It's subtracted.
Because we subtracted.
No.
If you first if you made the like 2x cubed minus 1 to the power of negative 1/2, then you would have addition.
It'd be yeah, exactly. So yeah, because it was division, that takes care of the subtraction, and then it's subtracting the bottom. So it's the top minus the bottom, so it'd just be the 1/2. Yeah. Is that clear? Okay. What else can we do?
You could break up the first one into an addition, and then and then you could move that.
And I'm going to actually go ahead, so I'm going to break this up because it's multiplication here, so it's natural log x plus, I'm going to put the 2 out front, 2 times the natural log of x squared plus 1. Minus, and then this 1/2 here can also go out front, natural log of 2x cubed minus 1. Wow, there it is. I don't know if I can scoot it out here some. Doesn't quite fit still. There it is.
Now, couldn't you split the first one into addition?
Yeah, that's what we just.
We just did. Yep, sorry. X times x squared plus 1, quantity squared.
I didn't even.
No, that's okay. I did a couple steps at once there.
You really made it great.
Like I said, this is our next to last one. We got one more after this one, then we're done. I know you guys are like, we should have been done 50 minutes ago. All right, promise. It's a lot. It's a lot. I understand. This is a lot today. I know, but I want to get through both, reviewing logarithms and then also get through the logarithm problems too. Sometimes I like to do too much at once. We'll see. Can we simplify this any further?
I don't think so.
No, not really. So now we can finally go about taking the derivative. Okay, and this is actually not too shabby now we've broken it up. Right before, now, not bad. Okay. So Donovan, what's the derivative of natural log of x? One over x, yes sir. Very good. Plus 2 times, what's the derivative of the natural log of x squared plus 1? Go ahead, Donovan, keep going there. What's the derivative of, so it's going to be, 2 times natural log of x squared plus 1, the derivative of that, I put the 2 times there. What's the derivative of natural log of x squared plus 1? Ooh, careful, we have to do 1 over. The derivative of natural log of something is 1 over that something. So it's 1 over x squared plus 1, then times the derivative of what's inside, which is just what? 2x, like you said. Okay. Minus 1/2 times, all right, now what about this one here then, Donovan? What's the derivative of natural log of 2x cubed minus 1?
1 over 2x cubed minus 1 times 6x squared.
Beautiful. Very good. Not too shabby. Not too shabby. We can simplify a little bit, right? So we get like 1 over x here. 2 times 2x is 4x, so 4x over x squared plus 1 minus, and then 1/2 times 6, that's going to become just a 3 there, so we get 3x squared over 2x cubed minus 1. And that is that. Okay, questions on any of that? Like I said, we got one more after this one, one more after this one.
Do you really want to go? Are you going to class?
What are you gonna do?
Okay, questions? I got one more here, guys, and then we'll be done. All right, and then you can have a break. And I'm going to write something here. So because the natural logarithm, listen up. Because the natural logarithm is undefined, okay, because the natural logarithm is undefined for negative numbers, you will often encounter, you as in the students, you will often encounter expressions of the form. So because the natural logarithm is undefined for negative numbers, you will often encounter expressions of the form natural log of the absolute value of u. You see the absolute values in there. The idea being that since we can't take the natural log of negative numbers, we put absolute values in there. All right, and here's the key thing. When you see, or when you differentiate functions, in the form y equals natural log of the absolute value of u, do everything as usual. So in other words, don't freak out when you see absolute values, be like, ooh, absolute values, I hate absolute values and I don't understand them and I'm going to stop. It's the same thing for natural log of the absolute value. It's the same thing as doing natural log of just u. All right, so let's, as an example here, let's find the equation of the line tangent to f of x equals natural log of the absolute value of 2 sine of 2x minus 3 at x equals 0. Alright, so you can see we have a function there with the absolute value. So we're like, ooh, absolute value. But we know that we can treat it just like it's, we can treat it, you know, when we go to take the derivative as just the plain old, as a plain old just natural log without the absolute value there. Alright. Christian, to write the equation of a tangent line, what do we need?
The derivative.
We need to find okay, so we find the slope using the derivative. So let's find that derivative here, Christian. Very good. So f prime of x is going to equal. We really can't simplify this at all, so that's why I went right into taking the derivative. Sometimes you can rewrite your natural log and do it that way, but we'll just have to take the derivative here. So, okay, what is that going to be? Derivative of natural log of something is 1 over that mess. 2 sine 2x minus 3 times the derivative of what's inside. So what's the derivative of 2 sine 2x? Well, it's going to be 2, right, because the 2 is just a coefficient there. What's the derivative of sine? Cosine of 2x. Ooh, but then we have to multiply by the derivative of 2x, which is just 2. And the derivative of minus 3, it's gone, right? That's why I didn't write the minus 3 there. The derivative of minus 3 is gone.
Wait, why don't you put the 2x in the cosine?
It's not in the cosine.
I mean the minus 3 in the cosine. Like, why isn't it 2?
Because when you take the derivative of this thing, the derivative of 2 sine 2x is 2 cosine 2x.
But, so it's not the derivative.
but the minus 3 goes away, because,
Oh, I put the,
yeah, sorry, it's just 2 sine of 2x. It's not 2 sine of 2x minus 3. It's just 2 sine of 2x quantity minus 3, yeah. Because when we take the derivative of 2 sine 2x minus 3, the derivative of sine is cosine, but it's cosine of 2x times then the derivative of what's inside, 2. Remember, there's 2x inside there. So the derivative of 2x is 2. Is it okay? Or are you just saying it's okay?
So, is there something inside from
What's the derivative of sine of 3x, squared? It's cosine 3x, I shouldn't put equals there. Cosine 3x squared times 6x. You still have to multiply by what's inside there, right? The derivative of 2x then is 2. This 2 is there because it was a coefficient. This 2 is here because it's the derivative of what's inside the cosine for the chain rule. Okay, sorry, moving on. All right, Christian, I got the derivative. Now what? How do we use the derivative to find the slope?
Need a y.
Do we need a y value? And my derivative, all I see are x's. So what do we have to do? Plug in 0. We want to find the tangent line at 0, so let's just plug in 0. F prime of 0 is 1 over 2 sine of 0, basically, minus 3, times 2 cosine of 0, basically, times 2. Okay, let's see here. Sine of 0 is 0, times 2 is 0, minus 3, so that's negative 1/3, times cosine of 0 is 1, times 2 is 2, times 2 is 4, so we get negative 4/3 is our slope. Okay. And so then, are we done here, Connor? Do we have all we need to write the equation of our line? I have a slope, and I have x equals 0 is my point. Is that enough to write the equation of the line?
We need a y value?
We need a y value, that's right. And how are you going to get that? Magic. Mathemagic.
Wait, so if you put that into the equation,
Yeah, not, what do you mean by that? This or this?
the first
This one.
No, you said the first.
I said this first, though, didn't I?
Yeah.
So it's the x equals 0. This is the x coordinate. What is this number? It's the value of the derivative, it's the slope. 0 goes back into the original function, so f of 0 equals natural log of the absolute value of 2 sine of 2 times 0 minus 3. Okay. 2 times 0 is 0. Sine of 0 is 0. 2 times 0 is 0. Minus 3 is, negative 3. So it's natural log of 3, right? Because it's natural log of negative 3, but then absolute value negative 3. So it's ln of 3. So then, now that we have our x-coordinate and our y-coordinate right here, Connor, what's going to be the equation for my tangent line in point-slope form, please? Y minus natural log of 3 equals negative 4/3, parentheses, x. Yeah, it's okay, x minus 0, that's right. There it is. Wow, there it is. Okay, great times. Such a party time. All right, sorry for that marathon there, guys.
I don't even know why I'm
Stop the video.